All right, so number 10 from yesterday. Okay, so if we take a look, I'm going to remind you again, it doesn't happen super often, but it does happen from time to time. Remember the very first thing you should always do, direct substitution. See if there is a limit that you can just find it directly by substituting in the number, okay? Because even on problems like this that look like they're a factoring type of problem, there are some problems that have the exact same look to it that you actually get an answer to. Okay, so just as a heads up, start there. This is not one of them. If you substitute it in, you get negative 64 plus 64, you get 0, and then you'll also get 0 in the denominator. So you do get that indeterminate form. So that leads us to either factoring or the conjugate. Okay, in this case, which one is it? Factoring. Remember, the conjugate ones are pretty much the square root. If you see a square root in the problem, pretty good chance it's a conjugate one. If not, it's probably a factoring one. So we talked about this previously. The top, the numerator, is, in this case, is a sum of cubes. You could go through and, if you remember, you can factor it as a sum of cubes. Perfectly fine. Again, I doubt very many people remember that, if anybody. So instead, if you don't remember, what can we always go back to? Synthetic division. We can always go back to synthetic division. It will work. So in this case, we're trying to find a as it goes to negative 4. We'll put that in the box here. And if we're factoring the a cubed plus 64, remember you're looking at the coefficients. And you have to go down 1 degree at a time. So we're starting with 1a cubed. We have 0a squared, 0a, and then a positive 64. Okay? Don't forget the missing terms. You got to make sure you're careful on those things. And now we do the synthetic division. Bring the 1 down. Multiply, I get negative 4. Add, we still have negative 4. Multiply, we end up with 16. Add, we still have 16. Multiply, I get negative 64. Add, we get 0, which is what you should get. Okay, which means negative 4 is a 0, which means the first factor then is a plus 4. Okay. Remember, your factor is always x minus whatever you used. That's why it turned into an a plus 4. Okay. The other factor, remember, is coming from the coefficients down at the bottom here. So there's your quadratic factor, which means you've got a squared minus 4a plus 16 as the second factor. And denominator, there's no factoring to do, so it just stays as a plus 4. And if you now take a look, we're looking at a when it's negative 4. The a plus 4s cancel out, which means the issue at negative 4 is no longer there. We don't have 0 in the denominator anymore. We don't have the 0 in the numerator anymore. Now, we can take negative 4 and plug it in and get your limit. Okay? So anytime you're working your way through any of these problems, once you've canceled factors, pretty good chance you probably eliminated the problem. Okay? And then you can directly substitute and get an answer for the limit. Any other questions? Anything else you want to go over? Devin? Okay, I was hoping somebody would ask about 22. Let's take a look. 22. All right, same thing again. If you directly substitute it in, you again are going to get 0 over 0. You substitute in, you're going to get negative 1/8 plus 1/8, 0 over 0. Okay, so again, this is another one of those. We don't have any square roots, so I don't have to worry about the conjugate. It's not really a factoring problem either. This is one of those complex fractions that you got to take a look at. And when we talked about this yesterday in problem number 21, remember the general, most of the work for this problem, ignore the divided by x to begin with and just focus on the numerator. You're going to try to get a common denominator so that you can combine those two fractions into one, because then you can simplify everything from there. Easiest way to go through and get a common denominator. Look at x minus 8 as one of your factors. Look at 8 as the other one. Multiply one fraction by the other denominator. Multiply the second fraction by the first denominator. Okay? Just multiply by the opposite denominator. So for example, in the first fraction, I'm going to multiply top and bottom by 8. In the second fraction, we're going to multiply top and bottom by x minus 8. And now you'll have a common denominator of 8 times x minus 8. Okay? That doesn't always give you the least common denominator, but that's okay. You can deal with the simplifying at the end. It makes the problem a little bit simpler. So if we take this numerator then, we've got, like we said, 8 times x minus 8. There's our denominator, our common denominator. If we look at the numerators now, first one we would have 8. Second fraction, you got the plus 1, which you would distribute. If that was anything other than 1, you distribute the number. If there was a minus sign here, you distribute the negative with it. Okay, but ultimately, you're taking that and distributing. Okay. So we end up with plus x and minus 8. We'll clean that up here in just a second. But there's the numerator now combined into one fraction. Keep in mind, this is still all over x. Okay. So it's a little better, but still pretty messy. I mentioned this to both of the other classes. I'll mention it to you guys as well, just as a heads up. When you have one of these complex fraction problems, it's super important to stay organized, because otherwise this gets pretty messy pretty quickly. Okay? So trying to keep it as organized as possible, not only on your paper, but kind of in your head as well as you're working your way through it. All right, so now if we start to make this easier, the numerator again, if we're looking back at that, we've got 8 and a minus 8. Those cancel out. So ultimately, all that stuff simplifies to x over 8 times x plus 8. Or x minus 8, excuse me. And anytime we've ever had a complex fractions inside a fraction problem, instead of dividing, we always multiply by the reciprocal. So instead of dividing that fraction by x, I'm going to multiply that fraction by 1 over x. And now, hopefully it's a little bit more straightforward. You've got an x in the numerator. You've got an x in the denominator. Those will cancel out. There's the canceling we were talking about before on the previous problem. Remember, the issue was when x equals 0. Well, now you no longer have 0 in the numerator or denominator. It just canceled out. Which means now we can plug the 0 in and get our final answer. We will end up, if you plug 0 into the rest of this, you're going to end up with a negative 1/64. And that's the limit for this problem. You get negative 64 in the denominator, 1 in the numerator. Like I said, the biggest part is you see most of the work is really cleaning up the numerator. Cleaning up the complex fraction really is the idea. Okay. Doing okay? Any other questions we have before we move on? Yeah. Okay. Take a look. We'll make this the last one. Actually, this will be a good one. Number 12. Okay, here it is. I say this is a good one because you're going to actually see this one's pretty straightforward, okay? It's pretty straightforward in terms of simplifying this down, but it's been a while since we factored again, so we'll refresh your memory on it. When you substitute 2 in, again, unfortunately, this is one where you do get 0 over 0 still, so you do have to factor, okay? Again, if this problem's on the test and you get stuck, synthetic division for the top, synthetic division for the bottom, and then keep going from there. Okay? Now, I'm glad that we're going over this because this one is actually fairly easy to factor if you recognize what's going on. All this is just a trinomial. Factor this the same way as if this was x squared minus 2x minus 8. It's almost exact same factoring. So if you take a look, Instead of x squared, where we would say, okay, x times x, you've got x to the fourth, which means we've got x squared times x squared. Okay. Factor the last term, 8. 2 and 4, okay. And you're trying to get a middle term, a negative 2. Therefore, you need a positive 2 and a negative 4. Done. It's factored. Just like you would, like I said, this is basically the same thing as x squared minus 2x minus 8. You factor it the exact same way. You just have x squareds instead of x's. Right? It's the exact same problem. And then, same thing in the denominator. Factor that as a trinomial as well. X to the fourth is x squared times x squared. Again, factors of 8. Once again, 2 and 4. But this time I need to get a negative 6x squared in the middle, which means both of those need to be negative. And oh, look at that. We have a common factor that we can now cancel out. X squared minus 4, x squared minus 4, those go away. And what's left, we can now substitute in directly and get our answer for the limit. Okay? The x squareds minus 4 will cancel out. Like I said, recognizing that this, by the way, this method is a whole lot faster than synthetic division on this problem. Because if you did synthetic division, it's only going to take you down to an x cubed. And off the top of my head, I think you're still going to have to go even further than that and do it again to get down to x squared. Okay? Which is the importance of recognizing that this is just factorable. Okay? It will get you to the answer a lot quicker than trying to do synthetic division. Okay? Okay. Let's move on then. If you have other questions, again, don't hesitate to, I think you're going to have a little bit of time at the end of the hour. You can ask individually there. Otherwise, you're welcome to come in during ELT. We'll take a look. We'll go through things. Whatever you need, I'm more than happy to help. But let's go into the actual lesson for today. Okay, so if we take a look, I told you before, the main difference between what we're doing today and what we have been doing is instead of finding a limit at a value, at 2, at negative 5, whatever, now we're going to let x go to the ends of the graph, positive infinity or negative infinity. Okay? The reason why it makes it a little bit more, I don't even necessarily want to say difficult, it's just different, is because notice, even though we were doing a lot of algebra in the homework, we were going through, and at some point, you could always just plug the number in. In this case, since we're going to infinity, can I plug infinity into an equation and get an answer? No. Not really. So this is much more, we're going to, by the way, kind of, but it's much more conceptual because we're dealing with infinity rather than 2. Okay? 2 is a little more concrete than infinity is. So that's where we're headed. All right, so a little quick review here. If we had to find the limit of 1 over x as x goes to 0. 0? Yes? No? We got an issue, right? If you take 0 and we plug it in, you get 1 over 0. Can't have that. And you can't really factor that. There's no factoring. There's no conjugate here. There's no square root. So we got an issue. And I don't remember if it was in this class or one of the other classes, but somebody asked me yesterday, what happens if you get a number over 0 rather than like 0 over 0? Okay, what if it's 1 over 0? What if it's 12 over 0? What if it's something along those lines? And the answer is the same every time. If you get a number over 0, that means you have a vertical asymptote at that point. That's what's going on. Okay, so let's kind of graph this just so you can use the graph and you can see it and understand it, and then we'll move away from the graph. So if we were to graph this, we can't plug 0 in, which means we have a vertical asymptote at x equals 0. Okay? So we have a vertical asymptote right here. And maybe you remember this, maybe you don't. We'll talk more about it in the lesson. You also have a horizontal asymptote at y equals 0. Okay? Remember back, we'll see if you at least vaguely remember back when we talked about when the degree of the numerator is greater than the degree of the denominator, or vice versa, or when they're equal. We talked about like different versions of when you have a horizontal one. It was way back, like I said, it was back in end of chapter 2. You may not remember that. It'll make a whole lot more sense now, okay? And then if we graph this, here's what the graph looks like. Okay, that's just a rough sketch of what's going on here. So here's the question I have for you. Let's start on both sides. RH and LH standing for right-handed and left-handed limits, coming from each direction, okay? So if we're finding the limit as x is approaching 0 from the right, where's the graph going? Where's y going? As we're coming from the right and we're approaching 0, y is going to positive infinity, okay? So the limit as x approaches 0 from the right is positive infinity. That's where that graph is going. What about from the left? Yeah, as we approach 0 coming from the left-hand side, the graph curves down to negative infinity, which means, based on what you know right now about limits, therefore, what's the limit at 0? Does not exist, because the limits on each side are not going to the same thing. Okay? Goes right back to the basic definition of a limit. In order to have a limit at a value, you got to have the limit on each side be the same. We don't, therefore the limit here does not exist. Okay? In general, by the way, I'll give you kind of a general rule here as well. Anytime you have a vertical asymptote, one side, your graph is always going to be going to like positives and negative infinities on each side. Okay? So just as a heads up, which means the limit more than likely does not exist at a vertical asymptote. That's the idea of what's going on. Okay? Now, the other thing I want you to notice, because here's where we're headed. Let's say that x goes to infinity. If x is going to infinity, this is where we're going now. What's the limit? What is y approaching? 0, right? It's approaching 0. What if we go to the other direction? What if x goes to negative infinity? Also approaching 0, which, we'll make a connection here in a second. Does it make sense that it's also approaching the horizontal asymptote? You have a horizontal asymptote, and as x goes to either infinity or negative infinity, it's approaching that value. That's where those rules I was talking about, that's actually where they came from. It deals with limits, but you didn't know limits at the time, so we couldn't really talk about it from a limit perspective, so we just had to give you some rules, okay? But that's what we're going to end up connecting is when we find the limit to positive or negative infinity, what you're really finding is where the horizontal asymptote is. Okay? So, with that being said, this you don't need to write down. This is, as a matter of fact, we already talked about most of this already. So where we were, 0, 1, negative 1, limits at a point, at an actual value. Where we're headed, like I said, positive and negative infinity. Not going to spend much time on that. Take a look at this one. So here's now, we actually answered this just now, but I want to answer it without a graph. What did we say the limit was as we went to infinity? What were we approaching? 0. Graph was approaching 0, right? Okay, so that is the limit. As x goes to positive infinity, or even if x went to negative infinity, it's 0. The question is, here's where we make our transition. How do I do that without a graph? Because that's what we're going to do. Because you're not going to have a graph for these. You're going to have the equation. So here's where the conceptual side of things come in. Okay? Here's where I said before, we can't really take we're plugging in numbers. Now, we're going to kind of plug in infinity. Okay? Here's what I mean by that. Let's say we took 1 and we divided it by infinity. Okay? Concept. Here's the idea. Okay? Here's where I'm going to relate it back, and it'll make sense where this is coming from. Let's say you had $1. $1. And you had to take that dollar and split it equally amongst every person in the United States. Every single person gets part of your dollar. How much does each person get?
Nothing at all.
0. That's a limit. That's the concept. What if I said, okay, and I say infinity, we're just talking about a big number. That's all we're talking about. I could put in 1,000,000 right there. 1 divided by 1,000,000 is basically 0. 1 divided by 1,000,000,000,000 is basically even closer to 0. Okay? 1 divided by 10,000,000,000,000, even closer to 0. Okay? So that's the concept of infinity. What if I did this? What if we had 3 divided by infinity? Still 0. Now you have 3 whole dollars that you're dividing amongst every person. Still basically 0. Okay? That's the concept that we're kind of trying to develop in this case. Okay? So, what if I asked you this question? What if I changed it to like 1 over x plus 3? Yeah, so what if I had this? Like, what if I had 1 over infinity plus 3? What is it? Somebody said it. Still 0. Think about it again. Think about this as, I always like to think about this in terms of money because it makes a lot of sense usually. If you're taking this in money in people, if you've got that dollar and you're splitting it amongst 1,000,000 people, if you now split it amongst 1,000,003, is it going to change much? No. Here's the point I'm trying to make by adding that 3 there. What effect does the plus 3 have on this? Basically nothing. We don't care about that plus 3. It's not going to have any effect on this when we're going to infinity and working on these huge numbers. Okay? That concept is going to come into play today. If it was a plus 5, it was a plus 10, really doesn't matter because we're talking about such big numbers that the other part of it is really insignificant. Okay? Make sense or questions? Okay. There's the concept. Now let me connect it one more piece here. We talked about this already. Now I'll just formally give you the definition and stuff. We said as x goes to infinity or negative infinity, we talk about the limits. What is y approaching? What it's approaching is the horizontal asymptote. Okay? So the first part is really like the mathematical definition. The second part is the explanation of that. Okay? So all this is saying is if x goes to positive infinity or if x goes to negative infinity and you find a limit, y equals that number is the horizontal asymptote. Okay? So if the limit is 5, you have a horizontal asymptote at y equals 5. If the limit that you find in your equation is negative 3, then you have a horizontal asymptote at negative 3. So that's the concept of how this infinity and horizontal asymptotes are connected to each other. I'll give you a second to write that down if you're writing it down. Like I said, you're just finding the limit of the function, and whatever that limit is where you have a horizontal asymptote. Horizontal asymptotes are also called end behavior asymptotes, because at the end, 2 ends of the graph, that's what the graph approaches, the asymptote. All right, so there's, again, still conceptual. We haven't gone into the details yet, the nuts and bolts of things yet. But one other quick thing, you do not have to write this down, you have this. Just a quick heads up, all of these properties we talked about the other day, that we said rather than adding the functions together and then trying to do the limit, break it into parts and then just add the limits or subtract or multiply or divide, all still hold true. Okay? Everything still, even though we're changing it to infinity, these properties are all still true. Okay? You'll see that in the example. All right, so here we go. Let's get into how we do this stuff. The limit as x is going to infinity of 5 plus 1 over x. The good news about these, by the way, even though they're very conceptual, there's not a lot of work, which means they go pretty quick if you get it. If you understand the concepts, they actually go pretty quick. Like, some people might already know the answer to this. Was it right? 5. It's 5. Here's why. Okay? The answer to this is 5. Here's the reason. Here's where the property, like I was telling you, I'm going to write this out. You don't have to do this in your assignment. You could go straight to the answer. But I want you to understand why it's 5. This is really the limit as x goes to infinity of 5 plus the limit as x goes to infinity of 1 over x. We can take that, that's one of the properties that we said was, rather than add the functions at the beginning, just find the limit of each part and add that together. Well, what's the limit of 5? 5. Remember we talked about that the other day? Any constant, it's just a horizontal line. It's always 5 or 2 or whatever the number is. So the limit of this first part, that's 5, plus, we just talked about this, what's the limit as x goes to infinity of 1 over x? 0. 5 plus 0, 5. There's your answer. No graph needed. Okay? Like I said, and you don't need to write this out. I did just a conceptual idea. I mean, did I give you guys the worksheets? Yep, for today? Okay. Here's the worksheet for today. Good luck.
Thank you.
Here's the worksheet. Good luck. All right, let me give you another example.
Is it like odds or something, or is it?
Oh, they'll be quick though. Like I said, it goes quick. All right, so if we take a look at this one. Have a good weekend too.
Thank you.
As you take a look at this problem, one of the other things that you also have to consider when you're doing these limit problems with infinity and negative infinity is the sign. Okay? Now, in this one, it's not really going to come into play, but I want you to still kind of understand what's going on here. As we take, if we think about actually substituting this in from a conceptual standpoint, what we have is 4 over negative infinity squared. Oh yeah, you're going to want that.
Yeah, probably.
All right, now have a good weekend. First question. If we had to worry about the sign, when we square the negative infinity, what sign would we have? It'd be positive, right? Because you're squaring it. But in theory, what's the answer?
0.
Still 0. Now you've got a really huge number on the bottom. Take your $4 and divide it by every person on the planet now at this point, is kind of what this is like. Everybody gets basically nothing. This is still 0 as a limit. Okay? Now, the last class was struggling a little bit with the concept of infinity. So one of the suggestions I gave was, if you're struggling with this infinity concept, just put a really big number in there. Take out infinity and put 1,000,000 in its spot. We're just talking about really big numbers. That's what we're talking about. Okay? So if that is more of a concrete kind of thing, use it. Okay? Do that if you need to. That's fine. Okay. Let's keep going. Another one. Come on. Come on. There we go. Now, there's not a lot of algebra involved, but there is some algebra involved in these as well. Minimal. Okay? Remember back where we said like that whole x plus 3, the plus 3 doesn't have any effect on this really? In the big scheme of things? When you're doing these limits to infinity, really all you care about is the highest degree power. Okay? That term. That's the only one you really care about. Because that's the one that's going to grow the fastest. Which means in this case, I don't really care about that one. It's not going to have any effect on this problem. Same thing in the denominator. Don't really care about that one either. It's not really going to have any effect when we're talking about infinity. 1 doesn't change much. So now we focus on what's left, the highest degree terms. Okay? And in this case, really you can just do the algebra, which means what would we do right here? Yeah, we just cancel the x's, right? And we'd end up with an answer of negative 5/2, negative 2.5. Here's why you can do that. Okay, let me show you why. The reason you can do that is, let's say we now substituted in our infinities, if you will. We'd have negative 5 times infinity over positive 2 times infinity. When we're multiplying by infinity, isn't that really growing at the exact same rate? Which means multiplying the top and bottom by infinity, isn't that really just 1? It's not really growing. One's not growing faster than the other. They're growing at the exact same rate. Which means the negative 5 halves is the answer, just like you're doing the algebra. Okay? Like x's would cancel, and you got your answer. Okay? Let's go a little bit further. Let's go a little bit more, just to see if we can keep developing the concept here. We've got this one, and I think one more example for you. Yeah. Okay, so first part. Anything I can cross out? Yeah, the plus 1, if we're going to take infinity and square it and then just add 1, that 1 has no impact on the infinity squared. Okay? Don't care about the plus 1. That's really the problem right there. Okay? Now, one other question, by the way. Somebody in the last class asked a really good question. They said, when does it matter? What if is plus 5 big enough to matter? Is plus 10, plus 100? Okay? And here's what I said. Here's how I answered that question. Let's say this was your denominator. Out of these 3 terms, which one's, if we're plugging infinity in, which one's growing the fastest by a lot? It's the only one that matters. Don't even care about that. Don't care about that. You'll always deal with the one that has the greatest effect on the problem. When you square infinity, it's going to grow a whole lot faster than just infinity. Okay? So therefore, you disregard all of the other stuff and just focus on the highest degree term because it has the biggest impact. Okay? All right, so here's where we're at. Which means now, let's say we did the algebra. What would I get? Simplify that. Yeah, y squared on the denominator cancels this out. You get 4y squared. Okay? Now let's theoretically plug in infinity. What's the answer? What is it? A lot. What do we call a lot in this stuff? Infinity. So realistically, this is still going to like positive infinity, okay? Because if you took infinity and square it, you get a whole huge number. You multiply by 4, it's still positive infinity. This would go to positive infinity, which means, by the way, if it goes to positive infinity, what's the actual answer? Does not exist. Okay? It's not really approaching anything. It's just going off to infinity, which means your answer is this one does not exist. Okay? One other quick heads up, because I want to make you aware of this on this problem. What if the 4 was negative? Then we'd say it's going to negative infinity, but still does not exist. Okay? But the only reason I mention that is because the sign does matter. If this wasn't like an infinity, if this was negative 2 versus positive 2, it matters. So you got to pay attention to the sign. Yes?
So like if it's like if the infinity on top's high or on the numerator is higher, it always does not exist.
Pretty much, yeah. Yeah. So I don't know if you heard that or not. The question was, if the degree on the top is greater than the degree on the bottom, does it always pretty much go to infinity and therefore does not exist? Yep. Which were our rules. That was part of the rules when we talked about it back in chapter 2. That's where, if you remember the slant asymptotes, that's where the slant asymptotes came into play. Because of this. Okay? You probably blocked that out of your memory a little bit on purpose. All right, last example. And I'll tell you guys the same thing I told the last class, and that is, if this is not making sense, because it is super conceptual, ask questions, okay? Keep asking. There's a reason why the test is not until next Friday. It's so that you have a chance to work through and ask those questions and make sure you're understanding this and fairly efficiently, okay? So don't just sit there and wonder, like, I don't get this, I don't know. Then ask, okay? Yeah?
Is that our last test?
No, you'll have one more. Second to last. That was the wrong answer, huh, seniors? Sorry. Yeah, you got one more. All right, so again, you don't have to do this. I'm going to write it out as 2 parts. Let's find the limit of the first fraction, and then the limit of the second fraction, and just add the answers. Okay? So really what I'm looking for here is the limit as x goes to infinity. Yeah, see if you can figure this out while I'm writing this down. See See if you can come up with an answer. I'll give you a hint, the final answer is not a whole number. It's okay if you don't get it, it's fine. Just want you to try. Okay, here we go. Oh, wait. Okay, wait. See if you can find the limit of the first one, limit of the second one. Somebody's got it. Here we go. First one, can I cross anything out? Anything that's insignificant in that fraction? Yeah, the plus 1. That's not going to have any impact on this. Okay, simplify. What do you get? X's cancel. You get 1 over 2. There's your first limit. Okay? There's the limit of the first part. 1/2. Because again, the x's are going both to infinity at the same rate. They're not one of them is not squared, that kind of stuff. So therefore they just cancel out. So 1/2 plus anything in the second one that I can cross out. Nope. Nope. Think about it from this perspective. If it doesn't make sense, I'm going to cross out the 3. But if that doesn't make sense, think about if you just FOILed this out. All this is x squared minus 6x plus 9. And we're right back to what we talked about before. The only thing that matters there is the x squared. Don't care about the 6x, don't care about the plus 9. That's the one that's growing, that's the term that when it goes to infinity, grows the fastest. Which means now, simplify, what's the limit of the second fraction? 3. And the final answer? 3.5. Just had to add the 2 together at the end. Okay?
So,
yep.
does having... No, actually.
Okay. Like I said, I know it's super conceptual. That's what makes it hard. The good news is there's not a lot of work to show. Okay? There's basically you're crossing a few things off and conceptually figuring out what's happening and you put the answer down. Okay? So, assignment for today, let me hand it out and then I'll explain just 1 or 2 things real quickly. And that'll be it. What do you want to do the last 3 weeks? I know you are. You're on a roll here. Keep it going. I know you don't, but you're doing good. All right. Take a look real quickly at the assignment. So it is all of them. Yes, I know there's 34 questions, but when you start getting the hang of this, you're going to go from one question to the next question to the next question. Like I said, it's not. This will maybe take you 15 minutes once you get the hang of it. Okay? Now, real quickly on numbers 1 through 8, let me clarify. Match the function with its graph using horizontal asymptotes as aids. Here's what they're telling you to do. Notice the equations 1 through 8 down below the graphs. What they're really saying is find the limit as x goes to either infinity or negative infinity, because that's where you have a horizontal asymptote. Then look at the graphs and figure out which one matches. Okay? So they're really limit problems that you're then looking at the graph to match the horizontal asymptote. Okay? Wanting to make that connection. So for example, number 1. What's the limit of number 1? 4. Now you look at the graphs and you say, all right, where do I have a horizontal asymptote that's at 4? And there's actually two answers. Be careful, by the way, because the scales are different on all the graphs. So it'll take a second. C or D should be what you're looking at. They both have horizontal asymptotes at 4, or at least approximately. So then the next question becomes, well, how do I know which one it is? Okay. It is C, and here's why. Notice on D, there's no value at 0, and at C, there is a value. So if you just took 0 and plugged it in, you get an answer. That's how you know it's C versus D. Okay? Because you actually have a value at C, and you don't on D. Okay? But really the main concept is the horizontal asymptote is the limit. That's the main concept on those. Okay? All right. You got a few minutes at least to get started, ask some questions, clean some things up, ask if you need some help.